Hi subscribers. Sorry that the pasta container is in the shop, but I can't get it out. So number 5. The first thing it asks is write down the expression in terms of m, v, and r for the angular momentum of the system. And so to find the total momentum of the system, you have to find the momentum of the bar and the momentum of the point mass. And so momentum of the bar we know is 0 because there is no angular velocity because it says it's unmoving. It gives that in the problem. And then for the point mass, we know that it is equal to I times W. And then for I, we know that it's equal to mr squared. So and then the mass of it is m over 3. The radius is r squared, and then velocity is equal to the radius times angular velocity. So solve for angular velocity and you get v over r, and then plug that in and you get m r squared over v all over 3r. R cancels out and you're left with m rv over 3 equals the momentum of the whole system. And then the second question asks, part A, I asks for the momentum of the system when it's moving. And so you know that still momentum is equal to I times angular velocity, so mr squared times is equal to all over r, and then add, that was of the bar, and then this is of the point mass to find the sum of the momentums of the system. And then r squared over r, and then r cancels out, and then remember that angular velocity is equal to v over r, and substitute that in. I just did that wrong. I just have to add them. Okay, so it's equal to 4/3 r v, which is equal to what it says in the problem it gives you, that it's 4/3 mr squared. And so then now we can put in that velocity is equal to the radius times angular velocity, r, and then substitute in r, and then r squared times omega. So it worked. Yay, they're equal. And then for the next part, it asks, hence show that the angular velocity is equal to v over 4r. So now that we know that this is true, we know that this is true because momentum is conserved throughout the system. This is the initial momentum, this is the final momentum. And look, the way I wrote it, we can cross multiply. Wow. I know it's not needed, but just let me live. And then now, I forgot the 4. solve for angular velocity. R crosses out. And then also have to note that what did I do wrong? Oh, I forgot the 4. So this is 12. Never mind. There we go. Now it's equal to 4. Now it's equal to 1. Boom, boom. So it's equal to 4 R. Yay, it worked. And then part B is where it gets fishy. Oh wait, just kidding, not there yet. Have to do part 4. So the energy lost. So first find the sum of the energy initially, which was equal to 1/f mv squared. And then again, velocity is equal to 4r omega, because earlier we found that velocity is equal to 4. And so that's for later though. For this, it's 1/2, and then the mass of the point mass is m/3, and then the velocity is equal to 4r omega squared, and this simplified is equal to mr squared omega squared over 3. Just trust me, it is. And then sum of the energy after the collision is equal to 1/2, because it's moving, it's rotating. And so 1/2, and then we already found the inertia, and it's 4/3 mr squared omega squared. And then this simplifies to 2mr squared omega squared all over 3. And then to find the change, do final minus initial. Did I do that right? Yes, I did that right. And so everything's the same, so 2 minus 1, and then boom. Wait, no, it's right. I don't know. And then for part B, okay, this is where it gets fishy. So we know this equals this, because this is a formula in the book. And then this is equal the momentum, and then the torque, it's in the problem, is 0.01, and then the inertia we found earlier